17 key points can map a person's pose in one forward pass. Let's build that pipeline with YOLO26. We are sharing the full article and code to reproduce the results in this video at the link in the description or pinned comment. To understand pose estimation, we have to look at what we're actually mapping. We define the 17 COCO human key points as anatomical landmarks, from the nose and eyes down through the shoulders and elbows to the knees and ankles. The crucial detail? Each predicted key point carries exactly 3 values: an x-coordinate, a y-coordinate, and a confidence score. This data forms our digital skeleton. The architectural contrast here is fascinating. Older top-down pipelines had to detect people first, crop the image, and then estimate joints. Bottom-up pipelines found joints first, but struggled to group them into bodies in crowds. YOLO26 completely changes the game by predicting both people and their key points together in one forward pass. That single-stage prediction gives us incredible efficiency. Let's look at the architecture. It relies on a triad. First, a feature-extracting backbone captures multi-scale image details. Second, a multi-scale neck fuses those features so we can detect people whether they are far away or right up close. Third, a dedicated RLE pose head pinpoints the key points. Plus, the source claims end-to-end NMS-free inference, dropping the complex non-maximum suppression step entirely for highly predictable latency. There are 5 YOLO26 pose model sizes, from Nano to X-Large. To be precise, the benchmarks are explicitly attributed to the COCO Keypoints Val 2017 dataset at 640 by 640 resolution, measured on an Amazon EC2 P40 instance with a T4 GPU running Tensor RT10. We're selecting the Nano checkpoint for this tutorial. It achieves a rapid 1.8 millisecond speed on that T4, giving us an ideal, lightweight foundation to execute our code. This video is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. All right, let's get our hands dirty. We're going to dive into a genuine, detailed code walkthrough straight from the article and the pinned companion notebook. Step 1 is setting up our environment with pip install ultralytics. Then we import our specific libraries. We're bringing in YOLO from ultralytics, CV2 for OpenCV, NumPy, OS, Shootle, zip file, and URL.request. From there, we define our workspace directories exactly as laid out in the notebook, setting up a work dir, input dir, output dir, along with the specific video output and image output folders. To cap off the setup, the script downloads and stages a public GitHub release zip, extracting all of the media files right into our input directory, so we're ready to roll. With the environment prepped, it's time to initialize. We set model name to YOLO26N-pose.pt and simply load it using model equals YOLO, passing in that model name. Like we just touched on, the tutorial intentionally chooses this Nano variant because it's incredibly fast on standard hardware, giving us a really snappy hands-on pipeline without needing a massive GPU array. Now that the model is loaded, let's actually feed it some images and see how we visualize the output. For single image inference, we pass the frame into the model using a confidence threshold of conf equals 0.5 to filter out the noise, and we set verbose equals false to keep the console nice and clean. Then we call results 0.plot. This is great because it gives us so much control. We can toggle Boolean arguments for boxes, labels, and conf, and tweak styling parameters like line_width and kpt_radius to make our digital skeleton look exactly how we want. Finally, we use OpenCV's ImWrite paired with the NumPy HSAC to stack the original and annotated images perfectly side by side. But what if you want the raw numbers? The source defines key point names mapped to the 17 indices. The actual coordinate data lives in result.keypoints.xy. This tensor has a shape of n by 17 by 2. N is our multi-person count, so how many people it found. 17 is for the joints, and the 2 represents the x and y coordinates. We also get result.keypoints.conf for the confidence scores. By setting up a simple per-person loop with a nested per-keypoint loop inside it, you can effortlessly extract every single coordinate for your own custom logic. And the results of this exact code are honestly super impressive. Looking directly at the demonstrated image results from the notebook, the model accurately tracks dynamic stances in karate and handles the really complex, twisted poses you see in yoga and acro yoga. It easily maps structural alignment in a gym, tracks standard walking gaits, holds up against extreme inverted bodies in gymnastics, cleanly separates overlapping bodies in group play, and tracks fast mid-air movements in sports action. The Nano model locks onto all of these complex scenes directly in a single pass.
Processing static images is cool, but applying this pipeline to video data frame by frame is where it really comes alive.
Our run keypoint on video function executes in a very strict logical order. First, we spin up cv2.videoCapture and check is opened. We read the video specs, FPS, width, height, and the total frame count. Next, we configure VideoWriter 4cc with MP4V and initialize cv2.VideoWriter. Then comes the workhorse, the cap.read loop. For every single frame, we call model frame conf equals 0.5 verbose equals false. We immediately pass that output into results0.plot using our plot quars, write that freshly annotated frame out, and finally cleanly release both the capture and writer objects. The notebook also shows off two really cool visualization variations. First is a dance side-by-side writer. Here, the output file is explicitly initialized at double the source width, so it can map the original and annotated frames side by side. The second is a progression grid for a file called dance2. The code grabs keyframes at exactly 10, 35, 60, and 85% of the video duration, scales them, and uses NumPy, HStack, and VStack arrays to build a 2x2 grid, visualizing the choreography over time. When you run this video pipeline, you get the specific results demonstrated in the article. You can see it tracking rapid arm strikes in boxing and mapping smooth transitions in yoga. It maintains a solid lock during chaotic urban movements in parkour and wide sweeping arcs in the dance clip. It accurately maps full extension in the jump video and flawlessly outputs that awesome 4-panel choreography progression we just talked about. And remember, all that's temporal flow is captured purely through consecutive, frame-by-frame inference. Now, as exciting as this is, we need to be very clear about the technical boundaries of this implementation so you know exactly what is and isn't happening. I want to state firmly what this notebook does not do. It performs simple frame-by-frame inference and visualization. It does not do temporal tracking or identity association between frames. It doesn't implement smoothing, interpolation, joint angle computations, rep counting, form assessment, or action and gesture classification. It is absolutely not a validated medical, safety, or production system. Also, the checkpoint strictly uses the 17 keypoint COCO human schema. If you want a custom or non-human schema, you're looking at full retraining. And finally, never present the source-reported latency benchmarks as a measurement from this specific notebook or as some universal real-time guarantee. The source is also very transparent about the observed limits of this single-stage architecture. You will occasionally see missed or misplaced joints in highly unusual or inverted poses. You'll definitely see tangled skeletons when overlapping bodies cause self-occlusion. It occasionally misses small or heavily occluded people in the background, and if you watch the jump video closely, there's a brief detection loss when the athlete is completely inverted. Understanding what a model can't do is just as important as knowing what it can do. Thank you so much for hanging out for this explainer. If this walkthrough was helpful, please hit that subscribe button. I'll leave you with one final thought. Since YOLO26 provides such a blisteringly fast frame-by-frame foundation, how might you engineer a lightweight temporal tracking or memory layer on top of it to solve those brief occlusions? The digital skeleton is yours to build on.